Hey everyone, my name is Austin James. I'm a graduate student here at K-State in the IMSE 841 course. My topic for this assignment is on support vector regression. We're going to take a look at where SVR came from and other topics related to using SVR. Today we're going to review a few topics. First, we will look at what support vector regression is and the various components of SVR. Next, we will review a data set and walk through a regression simulation in R programming, specifically comparing the performance of a traditional linear regression model to SVR. Within the regression simulation, we will introduce outliers to the data, and then we'll reevaluate model performance. To wrap it up, we will take a look at a couple practical applications for SVR. But to get started, we will take a look at something called support vector machine for machine learning to better understand support vector regression. Or support vector regression came from an early method of machine learning known as support vector machine. The support vector machine method for solving complex function estimation problems was originally applied to pattern recognition. SVM focuses on selecting a small subset of training data, and these are identified as support vectors. So in this image here, you can see that there are two sets of data, and the goal of the SVM is to classify these data by using these support vectors that lie on the edge of these margins. By optimizing the separation of just a few support vectors, the support vector machine method achieves this optimal margin and optimal separation of the entire data set, which ensures good generalization of the model. The goal of support vector machines are to optimize that margin utilizing the fewest support vectors. Within this margin is a hyperplane, which serves as the model's primary predictive function. Through identifying a small portion of data as training data, the support vector machine can then compare predictive results to actual data noted as test data. Um, Support vector machines work well for classification, and they can be used for machine learning and predictive capacities to identify previously unseen or unavailable data points. SVMs gave way to support vector regression as a means for machine learning for the purposes of regression analysis, time series analysis, financial forecasting, and other applications. While the goal of support vector regression is to obtain optimal generalized performance similar to support vector machine, SVR differs from SVMs through minimizing the observed training error to minimize the generalization error bound. So minimizing that margin that we saw earlier. Essentially, instead of relying on a few support vectors to separate large groups of data, which is done during classification, support vector regression relies on support vectors to optimize the error margins surrounding that central hyperplane. In doing so, many errors from data points are ignored, and only those data points outside the margin are penalized. Similar to support vector machines, support vector regressions do rely on a hyperplane that govern the predictive model. So this is an example of a support vector regression. We have the hyperplane. The line above and line below represents our error margin, indicated by the plus and minus epsilon. The plus and minus epsilon represents that margin within which many data points will lie. Those data points within this, what's called the epsilon tube, and those on the boundary are the support vectors that help train and ensure model generalization. Epsilon values will vary from a model to model standpoint, but the experimenter can modify the value of epsilon to align with the performance needs of the model. Um, we will take a look at a couple examples of how modifying the epsilon can impact model performance, or how modifying that can help achieve the predictive goals of the model. So there's a few impactful aspects of support vector regression that we're going to touch on. One of them are kernels. Kernels are impactful to performance of support vector regression. More specifically, when complex data sets require locating our hyperplane within a high dimensional feature space. There are four types of kernels that are applied within support vector regression: um, linear, polynomial, radial, which is the default and most efficient, and then sigmoid. Lastly, support vector regression provides excellent performance in the face of noisy data, and outliers have a reduced impact on support vector regression models. Next, we're going to take a look at a sample data set. We're going to review the data, and then we'll step through our R programming. We're going to be using the LM function in R that'll be applied to the data set, and review of the fitted values for predictions and the associated root mean square error values will be done. To that same data set, we're going to run the support vector regression. Comparisons will be made graphically between the LM and SVM results within R, as well as reviewing the SVR root mean square error values. Lastly, the data set, we're going to modify it a little bit. We're going to introduce outliers, and we're going to do a comparison of the root mean square error values before and after the outliers are introduced. We're going to go ahead and transition over to the R Studio programming. So before we get started in our programming and taking a look at the linear regression and support vector regression model, I'm going to do a little bit of background. So I personally am a licensed fire protection engineer. So I work on fire alarm, fire sprinkler systems for various types of buildings. We also do life safety analysis on certain types of buildings and systems as well. A big part of that is understanding how our smoke detectors and heat detectors operate under fire conditions. And we'll take a deeper look at or one of the real life applications once we get done with the programming. But I want to just introduce that. So the data set we're going to be looking at is going to actually include a few aspects of fire protection engineering. So it's going to have something called heat release rates. So depending on the size of your fire, the heat release rate will be smaller or larger. And then we also have data from heat detection and heat detectors that we're going to look at. So the way that the heat detectors work, we'll go ahead and open the data, take a look. So we have our time step, we have our heat release rate in column 5, and then the HD1, HD2, HD3 are essentially heat detectors that are located in different rooms of a simulation. Heat detector 1 is going to be in the room closest to the fire, the simulation fire. Heat detector 2 and 3 are going to be down a hallway and in another room. Um, and then so the heat detectors, they will register a temperature that will change over time. And then as the fire grows, the heat release rate value increases. And then our heat detector, the temperatures that they start measuring will again begin increasing. So this is the data set that we're going to be looking at. And we'll go ahead and step back through. So there's a couple things that we want to make sure we have loaded from our library. So ggplot is how we're going to be creating our graphs for comparison. Um, The library, the E1071, that is an R package that you can get from the cran.r website. This is necessary to um, run the support vector machine, or the support vector regression model. Has all the different components in order to run that. So we're going to go ahead and make sure those are loaded from the library. First thing we're going to do is we're going to go ahead and print our raw data, and we're going to take a look at what our raw data is showing us. So I mentioned, go ahead and increase this a little bit. The heat release rate is going to change over time. So the zero is when the fire is before the fire starts. As the fire grows, it follows what's called a t-squared function. So it's going to grow exponentially, and it's going to grow up to a point to where the heat release rate reaches its maximum. And in a real life scenario, it'll flatten out, and then it'll start to enter the decay period. So the fire will start to die down, and then the heat release rate will begin to drop. For this simulation, we just kept it constant once it reaches its maximum. The next thing we'll look at are the heat detector data. So again, heat detector temperatures. These are the heat readings over time. You can see they follow a similar progression. Fire growth begins here. The temperatures rise quickly, and then they begin to taper off as the heat release rate uh, reaches its maximum. This chart here is just to show you the relationship between the heat detector temperature reading and the heat release rate. So I mentioned that the heat detector temperature reading changes over time, but it also changes as the heat release rate changes. Over here, what we're seeing is the heat detector temperatures continue to increase at the point where the heat release rate has flattened out. Next thing we're going to do is we're just going to create some variables that we're going to use for our modeling. And so we're just basically assigning data points to certain variables in order to run our models. So x1, x2, um, the that x1 is going to be our time, x2 is going to be our heat release rate, and then y1, y2, y3, that's going to represent the outputs of each of our heat detectors. So the first thing we're going to do is we're going to run some code, run some lines of code for the linear regression model, and we're going to do it for each heat detector individually. So heat detector 1, heat detector 2, heat detector 3. So we're going to go ahead and run the first linear model. We'll take a look at some of the outputs here. And then in the summary, one thing I want to point out, the residual standard error, we'll take another look at this. That's the same thing as the root mean square error, so we'll take another look at that a little bit later. And then we're assigning the um, output of our linear regression model. We're going to plot our fitted values, which are going to be basically our predictive values. And we're going to take a look at how the predicted values of this linear regression model of each heat detector, we're going to take a look at how that performs, compare that to our data, and then compare that to our support vector regression. So I'm going to go ahead and run the same steps for heat detector 3 and heat detector 4. And so we've got our data, predictive data for the linear regression for those heat detectors. The next thing we're going to do is we're going to take a look at those fitted values, or those predictions from our linear regression model. So here, all of these dots, the red, green, blue. So we have our predicted heat detector temperatures based on our linear regression models. Uh, as you can see, we'll take another look back here. So I mentioned the heat release rate grows exponentially. And initially, what we're seeing in our predictive model is the linear regression model seems to be highly influenced by that exponential heat release rate growth. So we're seeing a somewhat exponential heat release rate, or sorry, heat detector temperature. in our predictive values. And at 500 seconds, that is where it's exactly where our heat release rate evens out. And so we're starting to see a linear relationship between the predictive values and the inputs. So the next thing we're going to do is we're going to do a linear regression fit for heat detector temperatures. And we'll see kind of how the performance of those linear regression models perform against the raw data of our heat detectors. So what we're seeing is the original data for each of our heat detectors, heat detector 3, 2, and 1. And then we're seeing the fit line of the linear regression models. So again, this fit line follows closely the predicted values. Um, and we can see that there's a pretty good gap there, pretty good gap on the top side. And so we'll take a look next at what our support vector regression models will look like. So when you're running support vector regression models, there's a few things that you can um, include. A lot of these are the default settings. So the default for this support vector regression model is going to be 0.1 for our epsilon, which again is that margin of error that we're going to be working with. The default kernel function is radial, and then the degree of is usually set to 3. And we'll see that the degrees changing that doesn't really make a big impact. So we'll go ahead and run these. And so that was the support vector regression model for heat detector 1. We'll go ahead and do heat detector 2 and 3 as well. And so the very next thing we're going to do is we're going to plot, similar to what we did for our linear regression model, we're going to plot our fitted values or prediction values of the 3 support vector regression models, and we'll see what those look like. So we can see here as well that the exponential growth of the heat release rate impacts the performance of our model early on. However, we see a change up around 300, 400, 500, 400 seconds. And so we can start to see where the support vector regression is doing a better job of not just being influenced by the heat release rate, but also trying to track along with the original data from our heat detectors. Next, we're going to take a look at pretty much all of it. We're going to plot our actual heat detector data. We're going to plot the fit of our linear regression models, and we're going to plot the fit of our SVR models. And we're going to do all of that in the same graph, and we're going to really quickly see how much better performance we get from our support vector regression model. Okay. So let me try to make this bigger. So again, dots are going to be our original data. We have our legend over here. So linear regression versus SVR regression for heat detector 1. So again, this is that original fit line we saw earlier. And this is the fit line that we are seeing from our support vector regression model. So as you can see, it much more closely follows the original data set. So it's going to have a better performance as far as predicting values of our heat detectors for a given heat release rate or a given fire size. Um, Same thing for heat detector 2 and heat detector 3, seeing similar performance comparisons of those. So the next thing we're going to take a look at are the root mean square error data. So real quick, I'm going to do a summary. I'm actually just going to go back to where's that? We're just going to take a look at heat detector 1. So we'll run our summary. So this is the summary of our linear regression model. I mentioned we're going to take a look at that residual standard error or root mean square error. So first thing I want to do is compare kind of our calculations to what the summary is showing us. And so that's what we're doing here is we're calculating the root mean square error of our first linear regression model. So we'll do that and we'll print that value. And so we'll see that the model summary was 48.85. Our calculations are 47.3. They're not exactly the same, but as far as being able to do a comparison, it looks like our math is relatively close to the model outputs. So the next step here we're going to do is we're going to take a look at our support vector regression our RMSE and see what that value looks like and compare that. So, and then we'll print that. All right, so we can see that the linear regression model root mean square error was a 47.3, and we're down at a 41.9 for our support vector regression. Um, the the really cool thing about support vector regression, and we won't get into that today, but there's some tuning that you can do, and the machine learning aspect of support vector regression that can basically would be the next step into fine tuning the performance, fine tuning the epsilon value, fine tuning the degree of the support vector regression, and it will greatly reduce that root mean square error value, and you'll get highly accurate predictive values out of that. So the next thing we're going to do is we're going to take a look at the same exact data except with some outliers introduced. And so I'm going to go ahead and clear all of this. Move my video. There we go. Clear the data so that we have a fresh start. And then we're going to run this. I won't view the data, but we will take a look at the raw data again. So that's our same heat release rate, no outliers in that. What we're having is outliers introduced into our heat detector temperature readings. And that's going to slightly impact our model performance. So um, let's see, go ahead and step through these. Again, we're going to assign all of our data points, and I'm just going to go ahead and real quickly um, run all of this. So run that and take a look here. So again, the outputs of the linear regression model look relatively similar to the last one, so it doesn't seem like the outliers are having a huge impact right away. But we'll go ahead and run our support vector regression models as well. Um, take a look at that. So again, outputs follow the same or similar trajectory. We can see here we have a little bit more separation on our support vector regression model, whereas before it followed more closely to those lines. And we'll go ahead and take a look at the root mean square error. So let's go ahead and run this and then come back down here and run this. So before our root mean square error was 48 for the linear regression model. Um, Now we're up at a 53. Our calculations indicate 51. The root mean square error for the support vector regression previously was a 41. So we'll take a look at that, and we've only gone up to a 44. So um, similar similar increase as far as the errors are concerned. But again, once you do the fine tuning, um, those are going to change quite a bit. The next thing that we want to look at are changing the epsilons. And so what I'm going to do is I'm going to increase for heat detector one, I'm going to increase the epsilon by a factor of 5. And then I'm going to decrease the the epsilon of heat detector 3 model by a factor of 5. So we're going to do 0.02. So we're going to rerun our support vector regression models. We're going to get new data, new predictive data, and then we'll take a look at that. Go ahead and jump to this one. So the first thing we notice is this heat detector one where we increased the epsilon by a factor of 5, jumped way down. It was up closer, much tighter to this data, but the hyperplane dropped. And the reason for that is I mentioned that our margins are formed by the value of our epsilon plus and minus, positive, negative. So what happened is as our margin widened, the line for our epsilon, let me just grab this. All right. So our margin widen, and what's happening is the goal of the support vector regression is to have as many points or um, uh, yeah, have the support vectors on the edge of our margin. And so what it's done is it's shifted the hyperplane down such that the boundary is closest to some of these data points. And similarly, on the bottom side, it's trying to pick up some of these points down here. It's trying to get closer to some of these data points on the bottom side, on the lower side. And so it's widened that margin and it's dropped that as well. Um, Conversely, what's happening is on the heat detector one, where we shrunk our margin, we made our epsilon tube skinnier. It's kind of taken more of a linear regression shape. It's gotten closer to the outputs of our original linear regression model. And what it's doing is it's essentially trying to overfit the model. And so you got to be careful when it comes to assigning the epsilon values, and you definitely have to understand how changing those can impact your model performance. And then well, actually, as far as changing the epsilon values, we're going to take a look at one of the um, real life applications and how they're handling that. So we're going to jump back over to our PowerPoint here in just a second to go ahead and take a look at a couple real life applications. I mentioned that the data we looked at was from heat detector data for a given fire scenario. I'll share my sources here in a minute, but NIST is actually working on a version of a machine learning algorithm using support vector regression with the goal of predicting flashover in residential homes. And what flashover is once a room or a compartment reaches its critical heat release rate and critical temperatures, all of the gases in that room, the smoke and off gases from the fire, they essentially ignite simultaneously, resulting in an explosion. NIST is working to try to be able to predict when flashover can occur and better inform fire department personnel when they're like arriving to a scene, things like that. This chart here shows kind of some of the data and the phases that NIST is looking at. So phase one is a set of temperature data that they're using and analyzing, and then they'll step through the phase two and phase three. So for phase one, they have heat detector one and heat detector two registering temperatures. After phase one, heat detector one is assumed to have been lost, so we're no longer obtaining data, but they're using the predictive performance of support vector regression during phase two to continue modeling data from that heat detector. And then you can see that heat detector 2 is still picking up data. After phase 2, heat detector 1 and heat detector 2 are both using predictive data, and heat detector 3 is the one that's still actually measuring temperature data. And then phase 4, we can see it's the model is putting out all predictive values. And so the goal is using actual data up to a point where the heat detectors are anticipated to no longer function, and then use the accuracy of the support vector regression as far as predictive values to continue simulating heat detector temperature increases until they can get to a point to say flashover will likely occur at this point after this much time, and then go from there as far as evaluating their model performance and things like that. Another example is there's a group in Hong Kong that are looking at modifying and adjusting the epsilon margin around the hyperplane, and they're looking to do so to create an asymmetrical margin. So what we looked at, the plus minus epsilon were equal, and we had the hyperplane was centered within our epsilon tube. The benefit of being able to create that asymmetrical margin would be instances where um, there's consistently conservative financial forecasting. So having the ability to shift your margin up or down, or basically prioritize data that is higher or lower um, than the prediction models, will allow you to reduce either upside or downside risk depending on your application. So this graph here is a result of modifying those epsilon values. That dashed line is the actual data. Red solid line is the predictive values, and then you can see just a little bit the wider margin of the error margin there. Um, and so, yeah, I just think it's really interesting. Here's some of the sources, some of the original papers by the people who originally pioneered support vector machine and support vector regression. And then the paper from NIST is where we kind of got started as far as our data and our support vector regression model. Thanks for listening, and hope you guys have a good weekend.